Okay, hello everyone. My name is Huolin Xin. I'm an associate professor at UC Irvine. It is a great honor. It's absolutely fascinating for me to present a short award talk on the new research direction running in my group. Today, I will present on machine learning enabled imaging science and materials engineering. So my group focuses on three directions. First, we work on artificially intelligent TEM, tomography, and yields technique development. Second, in the energy materials domain, my group focuses on two directions. One is making high energy lithium-ion battery using non-critical materials. There's a no cobalt cathode material that came out of my group that has extremely promising performance. We also work on extreme high rate materials, lithium sulfur battery, and solid state batteries. The second research thread is energy. In energy is on small molecule activation by atomic dispersed catalysts, and you invest heavily in this direction, as you can see here. Right, so the problem with machine learning in the TEM field is that there's a lack of ground truth label data sets for training useful machine learning models. To fill this gap, we have created a TEM ImageNet project. We have an ImageNet for atomic resolution images, where we provide 10 different types of ground truth labels given here for training super resolution, column masking, denoising, and localization. So here are some of the results from the baseline models we trained by my group. So we can see the super resolution net works really well, and the localization of columns work really well as well. So to put it in a real world test, we have benchmarked the super resolution net on some of the under-resolved images of Spinel Cobalt 304 images. The three atomic columns are under resolved here. After the processing, they show up very clearly with high certainty. So the most important thing is that for high precision atomic column localization, our method actually outperformed the 2D Gaussian fit by 20%. The 2D Gaussian fit is considered the gold standard in the field. To break this record by just our baseline model shows that our TEM ImageNet project could greatly impact the field. So you're welcome to use our training data set to actually create better models. Right, we have applied our atom segment models to real world application. Here's one example where we can clearly resolve the O1 and the O3 phase boundaries in the high nickel content cathode material for lithium-ion batteries. These phase boundaries and transition have never been reported before. Here's another example where we image the chemomechanical degradation of high nickel content materials at elevated temperature to resolve the atomic scale transformation due to oxygen loss. You can see here the transformation can be tracked at the atomic scale. Most importantly, we have uncovered a previously unknown two-step atomic scale process. Basically, for the O1 faulted phase to lose oxygen, transform into the rock salt phase, first, what happens, the transition metal needs to hop down to the lithium layer, and then it shear into the O3 stacking. This observation is supported by the analogy elastic band calculation, showing the barrier for nickel to hop to the lithium layer is lower in the O1 faulted phase than the regular O3 stacking. Of course, we don't only work on projection imaging. Here is the slide to summarize some of the state-of-the-art development of artificial intelligence enabled information in painting and artifact removal for electron tomography. We create a Tomo field net and Tomo diffusion net, and we're working on Alpha Tomo, and we show that the resolution of atomic electron tomography can be pushed down to 0.7 angstrom with deep learning assisted information restoration. Which is really impressive. And we have applied this technique to the imaging of the grain boundary of FCC metals. We found that unlike the conventional description of grain boundaries that have translational symmetry, the high-angle grain boundaries can completely lose the translational symmetry due to the curvature and undulated curvature related to the configuration of the structural units. So we can only see this by atomic electron tomography. And even more interesting, the development of a low-dose bright field TEM. Head up stem is really good for quantitative imaging of thick and heavy materials. However, for light elements such as carbon, graphene here, bright field TEM has its own merit. Due to the bandpass contrast here, we're able to reconstruct the wholly graphene structure that wrap around a very small nanocluster that shows all these holes that are active sites for this catalyst. So I was trained as a physicist in David Moller group. The reason that I became interested in energy storage and conversion materials and electrochemistry in general is because of my collaboration with Tito Abruni and Dilly Wan. Basically in 2012, this Nature Materials paper, we together resurrected the field of intermetallic catalysts, and particularly for the oxygen reduction reaction. This paper has been cited 1,000 times. Since then, my group has been focusing on the direction to create low PGM intermetallic catalysts for PEM fuel cell. And of course, after I moved to UC Irvine about 3 years ago, I wanted to shift the direction a little bit to work on non-PGM catalysts. One of the things that we can do is to learn from nature. Basically, billion years of evolution give us these enzymes, for example, the nitrogenous enzyme that has the single moly centers that can fix nitrogen in ambient pressures. So we can, what we want to do is create a synthetic version of them and having them anchored down on solid support so we can run heterogeneous or electroheterogeneous catalytic reactions. So if we go back 10 years, many people will ask, are you sure you have single atoms? Are they really doing the work? Are you sure you don't have any small cluster to actually catalyze these reactions? Now it's not a question anymore because the tools that my group specialize. For example, X-ray absorption spectroscopy here give us very good answer because it correlates well with the single atom loading. As you can see here, on the horizontal axis, the moly content as you increase as it increases, the ammonia yield rate actually increases linearly until it hit a certain threshold, it starts to plummet. That's because at that point, it starts forming small clusters, and we can actually correlate this activity results with the bulk results measured by XAF loading series. If they correlate well, that means you have atomic dispersed active sites that are actually doing the catalytic work. So, and of course, verify that with my expertise, which is transmission electron microscopy. As you can see here, all these atomic dispersed sites very well maintained even after agent use. Here, so these are the 4 catalyst system that my group has delivered. The zinc coordinated 4 nitrogen, really good for CO2 reduction. Was published in JAX recently. We have dual atom dimers. These are dimers that are materials that are extremely difficult to synthesize. They are for the nitrogen reduction reaction. The moly and the manganese active sites are for nitrogen reduction as well. So, all right, so where will my group go next? So my group is actually very ambitious to start this periodic table project. This is where we really want to make an impact. We want to let everyone know whether there are unified principles that govern the formation of, and the structure and the coordination structure of the single atoms. So right here are some of the examples here that actually we have more than 30 single atoms that are anchored down on this solid support. So in the energy storage domain, we have opened up a few new directions, including the development of a liquid electrolyte solid polymer electrolyte, with a focus on understanding and engineering the solvation interface structures. We also leverage functional materials such as ferroelectric materials to accelerate the migration of zinc ions or any ions for multivalent metal anode batteries. So in terms of hard materials development, we have built an AI platform for high-throughput synthesis of sodium cathode materials. Here the problem is that we lag behind in terms of publication because we discovered too many good materials. We apply the high throughput approach to the synthesis and the spectroscopy study of layer cathode material lithium-ion batteries, and also to the in situ diagnostic studies and high entropy alloys and ceramics. And this approach is extremely important for deciphering the local coordination structure of a single atom catalyst for this periodic table project. Last but not the least, we have developed a series of models, machine learning models, extract oxidation states, decomposition, octahedral, tetrahedral decomposition for the spectroscopy data. The thing is, it does not rely on absolute value of the echelon set. It does not need a background subtraction. So here, I want to end this talk by thanking all the funding agencies, students, postdocs, and collaborators. So without their support, I can't do any of the work. In addition, I want to shamelessly advertise advertise that we're actively hiring students and postdocs. If you're interested, please contact me. Now I'm going to hand my mic back to our president. Thank you.